Hello students. So welcome to this class. So up until last lecture we looked into Riemann integrable functions, their definition, and several properties associated with a Riemann integrable function. For example, if your function is continuous, then it is Riemann integrable. If it is monotonic, whether it is monotonic increasing or decreasing, then in that case also it will be Riemann integrable on the given interval. We also looked into the definition of of the fundamental theorem of integral calculus. We also looked into the definition or the statement of first mean value theorem and second mean value theorem. The theory of Riemann integrable function is anyways too extensive, but I try to compress it in a how to say shorter format. Now, based on the theories which or the theorems which we learnt in previous classes, today we are going to work out a few examples, and we will see that how we can be able to show that whether a given function is Riemann integrable or not, how we can calculate upper integral sum and lower integral sum of a given function. So today's lecture will be all about the examples on Riemann integration. So let me start. All right. So our first example is. So the first example is for the integral 0 to 1 x dx, we will calculate. So for the integral this, find the upper and lower integral sum on 0, 1 by dividing it into 3 subintervals. So that means our partition will have 4 points, and those 4 points will constitute our how to say 3 subintervals. Now it's obvious that if you divide the interval 0 to 1 into 3 subintervals, then your partition points will be 0, 1 by 3, 2 by 3, and 3 by 3, which is 1. So let P be the partition of 0 to 1 such that our partition P will be 0, 1 by 3, 2 by 3, and 3 by 3, which is 1, such that, and so this is basically our partition P, and the subintervals would be 0 to 1 by 3. So the subintervals are, the subintervals are 0 to 1 by 3, 0 to 1 by 3 to 2 by 3, and 2 by 3 to 1. Now if we look into the definition of upper integral sum and lower integral sum, which are basically UPF and LPF, so UPF is given by a formula of this type. So upper integral sum UPF is given by a formula of this type. Since in our case n is the number of subintervals, and in our case n is basically 3, because we have 3 subintervals. So r will be running from 1 to 3, capital MR times xr minus 1. This is our upper integral sum, and our lower integral sum LPF will be sum r running from 1 to n, small mr xr minus 1. So in this case n is 3, so we'll substitute n equals to 3, small mr times xr minus 1. Note that capital MR and small mr are the supremum and infimum, or upper bound and lower bound of the function f, which is x here in these individual subintervals. So let's name this equation as equation 1, and let's call this equation as equation 2. So next we have to calculate the upper bound in each one of these subintervals. So we have fx, so we have fx equals to x, and from here our capital M1 is basically f of 1 by 3, because fx equals to x is a monotonically increasing function in the interval 0 to 1, and therefore the maximum value of this function fx would be attained at the point 1 by 3, because at all the other points at x equals to 0 the function will attain its minimum value, and so on. So the maximum value of this function fx equals to x will be attained at the end point x equals to 1 by 3. So what will be the maximum value, or the upper bound of this function at 1 by 3? It's 1 by 3. Next we can calculate M2. M2 will be again attained at this end point 2 by 3. So it will be attained at 2 by 3 because the function is monotonically increasing, and the points are increasing again. So in this case the maximum value or the upper bound will be attained at this end point. So we can calculate the maximum value as f2 by 3, and f2 by 3 is again 2 by 3, and capital M3 is the maximum value of the function f, which is again attained at x equals to 1. So at f1, so this will be 1. Similarly we can calculate small m1, so we can write similarly small m1 equals to the infimum of the value at x equals to 0, because in this interval the infimum or the lower bound is attained at x equals to 0. So we can write f of 0 is 0. Next we can calculate M2, which is the infimum or the lower bound. So this is again attained at, let us go back to this slide. So the lower bound of this function f will be attained in this interval at the point x equals to 1 by 3. So we can calculate the lower bound at x equals to 1 by 3, which is 1 by 3, and what is that, and M3. So M3 is the lower bound of this function f in the interval 2 by 3 to 1. So this will be attained at f equals to 2 by 3, which is basically 2 by 3. So now that we have all these ingredients, we have to calculate x1 minus x0. So x1 is basically 1 by 3 minus 0, which is 1 by 3. Similarly x2 minus x1 will be 2 by 3 minus 1 by 3. So this is again 1 by 3, and x3 minus x2 will be 1 minus 2 by 3. So, this is basically 1 by 3. So, since we have divided the interval into 3 equal parts, these are basically the length of every subinterval, and it is pretty much clear that if you have divided an interval into 3 equal parts, then in that case the length of each one of these subintervals would be 1 by 3, because your interval is from 0 to 1. So, that is what we are getting. X1 minus x0 equals to 1 by 3, x2 minus x1 equals to 1 by 3, and x3 minus x2 equals to 1 by 3. So, now we are ready to calculate our upper integral sum. So, upper integral sum is sum r running from 1 to 3 capital M r times x r minus x r minus 1. So, if we substitute the above values, then it will be capital M1. So, first of all we can expand this summation, x1 minus x0 plus capital M2 times x2 minus x1 plus capital M3 times x3 minus x2. Is it clear? So, now M1 is capital M1 is 1 by 3 times x1 minus x0 is also 1 by 3, capital M2 is 2 by 3, x2 minus x1 is again 1 by 3, capital M3 is 1, and this one is again 1 by 3. So, we take 1 by 3 common, this one is 1 by 3 plus 2 by 3 plus 1, and this will be ultimately 2 by 3. And similarly we can calculate LPF, which is our lower integral sum. So, this can be given as r equals to 1 by 3 small m r times x r minus x r minus 1. We expand in the similar fashion, small m1 times x1 minus x0 and so on. So, our small m1 is 0 and x1 minus x0 is 1 by 3 plus small m2 is 1 by 3 and x2 minus x1 is again 1 by 3, then small m3 is 2 by 3 times 1 by 3. So, we can take 1 by 3 common, this is 1 by 3 plus 2 by 3. So, ultimately we will get 1 by 3. So, this is our upper integral sum. So, LPF equals to 1 by 3 and UPF equals to 2 by 3 are our respective lower integral sum and upper integral sum which we wanted to calculate. So, this is how we can calculate the upper integral sum and lower integral sum. We have seen several times that all we have to do is to find a partition of the given closed interval, and you need to calculate the upper bound and lower bound of the function in those subintervals and then put it in this formula. So, this is basically the formula, and that will give you the UPF and LPF of a given function. So, I hope you were able to understand this example, and will probably have such kind of examples in your exercise or in your assignments, and hopefully that will make the concepts even more clear. All right. So, now that we have looked into LPF and UPF example, let's consider an example where we actually say whether our given function is Riemann integrable or not. So, example 2. Example 2 is if f(x) equals to 1 for 1 less or equals to x less or equal to 2 and 2 for 2 less or equal to x less or equal to 3, then evaluate 1 to 3 f(x) dx. So, first of all, the given function is f(x) equals to 1 between 1 to 2 and f(x) equals to 2 between 2 to 3. So, obviously, it is a discontinuous function at x equals to 2. Now, having just one point of discontinuity would not create any kind of problem. I mean, you can still talk about Riemann integrability. Remember, all we have to have is whether the function is first of all the function is bounded or not, and second of all I mean if it is monotonic, then in that case also we can say that the function is Riemann integrable. So first of all here, so here our fx is bounded on 1 2 3 and it is monotone, and it is monotone there, right, which is obvious. So between 1 to 2 it's 1, and then between 2 to 3 it's 2. So obviously it's a monotone function with one point of discontinuity at the point x equals to 2, and therefore the theorem or the properties which we studied earlier, that if a function is monotonic, then in that case it is Riemann integrable. So by that theorem you may have to look into the number. So then by previous theorem I would expect you to write that theorem number here, or so by previous theorem fx is Riemann integrable, right, on 1 comma 3. Just look into that theorem which says that a monotonic function is Riemann integrable. So with the help of that theorem we can say that this function is at least Riemann integrable. That means this integral here, it makes sense that if someone asks us to evaluate such kind of integral, first of all we have to make sure that whether the function is integrable or not, whether the integral exists or not. So since by this theorem the integral exists, we can now calculate this integral. So how do we calculate? So to calculate, we can write the integral 1 to 3 fx dx. Now remember, 2 is the point of discontinuity, so we divide the integral into two sub-integrals at the point x equals to 2. So x is running from 1 to 2 fx dx plus x is running from 2 to 3 fx dx. Now between 1 to 2 fx is 1, and between 2 to 3 fx is 2. So if we calculate, then this is basically x from 1 to 2 plus 2x from 2 to 3. So this will be 2 minus 1 plus 6 minus 2. So ultimately it's 5. Sorry, this one is 4, so it will be 4. Yeah, it's 4, so 6 minus 4, and therefore this will be 3. So the answer is 3. Yes. So you see, first of all we have to check whether the given function is bounded and monotonic or not, or whether it is continuous or not, so that we can at least talk about that the function is Riemann integrable or the integral at all exists. And once we have that, then we can calculate the integral the way we please. So this is how to say one such example where we use those theorems. Now next we will move to, let's go to new page. Now here an example, another example. So another example is given a function fx defined by fx equals to x square when 0 less than x less than or equal to 1, and root x when 1 less or equal to x less or equal to 2. So then we have to find out what is, so evaluate 0 to 2 fx dx. So here our given function f is x squared between 0 to 1 and root x between 1 to 2. So obviously this function is continuous from 0 to 2, and therefore we can use that continuity theorem that every continuous function is Riemann integrable. So we can write x square and root x are respectively integrable or Riemann integrable in their respective range since they are both continuous, right? They are both continuous. It's very obvious to see that. So that means the function f is continuous, and if the function f is continuous, then this function is Riemann integrable. So also f is continuous on 0 to 2. So at least the continuity part is settled, and if the function is continuous on that interval 0 to 2, then obviously it is integrable, Riemann integrable. So let's calculate the Riemann integral. So since we have two different functions from 0 to 2, we can divide the range in two parts, fx dx. So we have divided the range or the limit, how to say, the interval 0 to 2 into two parts. So after division it looks like this. So one whole integral is divided into two sub integrals. Now we can write it as 0 to 1. Between 0 to 1 it's x squared dx, and between 1 to 2 it's root x dx. So this will be x cubed by 3 from 0 to 1 plus this will be x half, so it will be 2 by 3 times x to the power 3 by 2, yes, from 1 to 2. So then we can calculate these, and after calculating we will be able to obtain this as 1 by 3 plus 2 by 3 times 2 to the power 3 by 2 and minus 2 by 3. So this will be, I believe, 4 root 2 by 3 minus 1 by 3. So we can calculate whatever this is. So I leave this up to you. So you can see here the given function f was actually given by how to say, two different functions. So f is of course it is continuous, but it is given with the help of two different functions, and all we have to check first of all whether they are continuous or not. If they are not continuous, or if there is even one point of discontinuity, then we check whether they are monotonic or not, and if they are monotonic and bounded functions, then they are Riemann integrable. However, in this case we are very lucky because both the functions are continuous in their respective range, and therefore the function f is continuous, and if the function f is continuous, then it is Riemann integrable. So here I can write a small point, f is Riemann integrable. So f is Riemann integrable, and now we can calculate the integral from 0 to 2. So and this will be whatever you get after the calculation here, that will be your answer. So 4 square root of 2 by 3 minus 1 by 3 would be your answer. So this is one such example. Now what I'm talking about is with this discontinuity part, that let's say you have 1 point of discontinuity, or if you have 2 points of discontinuity, then what would happen to the Riemann integrability of the function. And in order to do that, we have a small theorem which talks about these finite points of discontinuity. And even though if you have finite points of discontinuity, you can still talk about the Riemann integrability. So let us state a very small result, or a properties. So the result goes like this. I would list it as property. All right. So property. So it says that any bounded function, which is continuous except for finite number of points. So that means it is not continuous at these points, is Riemann integrable. So if you have a bounded function which is continuous except for finite number of points, that means there are finite number of points where the function is not continuous, even in that case your given function would be Riemann integrable. There is a little bit generalized form of this theorem. So the generalized form goes like this. If a function f(x) is bounded on the closed interval a comma b, and the set of its points of discontinuity has only a finite number of limit points, limit points, then also f is Riemann integrable on a comma b. So that means if you have a given bounded function on a closed interval a b, the set of points where the function is discontinuous has only a finite number of limit points, and then in that case the function is also Riemann integrable. So it's in a way a modified version of the previous theorem, and we will see via some example in our next lecture what do we mean by these two theorems, and how can we apply them. So today we'll stop here, and in the next lecture we will continue with the examples on Riemann integration.